Hello everybody, my name is Yotam Gershon. I'm a graduate student at the Department of Electrical Engineering in the Technion Institute of Technology in Israel. I will present this work that was done with Dr. Yaakov, Buchris and Professor Cohen from the Technion as well. The title of this work is Greedy Sparse Array Design for Optimal Localization under Spatially Prioritized Source Distribution. We will begin with a brief overview of our work. The topic is acoustic source localization, which means estimating a source location using a microphone array processing. The challenge is that in noisy environments, the performance of the localization degrades. The solution lies by using different array constellations, which give better resilience for the localization. For example, we will demonstrate the localization performance using two different array constellations. In each of the figures, the axes represent the space. The source location is represented by the blue circle. The microphone array positions are represented by the black squares. And the estimated location is represented by the red cross. As we can see on the left, the bed constellation, a uniform linear array, in which the estimated location is pretty far from the actual source location. In comparison, on the right, a better constellation is three distributed subarrays in which the source localization lies very well on top of the actual localization. So our problem is how to design an array for optimal localization performance when the number of microphones is limited, which means sparse array design. The deployment is constrained to a certain region, which is useful when we want to design a practical array and we cannot place microphones wherever we want. And third, we have a priority region for localization performance. For example, a design problem can be when we have only 9 microphones to use. The array should be deployed in some corner of a room, and the localization is needed for the center of this room, which corresponds to some range of angles with respect to the array. In our work, we first introduce a new measure to quantify the expected performance of localization. And then we use it to introduce a new greedy algorithm to choose the best microphones from a predefined grid, such that the performance will be as optimal as possible. So we will begin with a short background discussing acoustic source localization in general and steered response power as a specific method. We will then present our work describing the motivation, the new measure, and the new algorithm. And we will end with performance analysis to our method, describing the simulations that were done and the comparative results. The problem formulation of acoustic source localization is as follows. A signal S of t is generated by a source located at unknown location Rs. The signal is then received in an array of M synchronized microphones located at known locations R1 to Rm. The localization is then performed based on the different propagation time from the source to each microphone. More formally, the mathematical model of our problem is as follows. The clean signal that is generated by the source is propagated to each of the microphones, indexed by M, with a propagation delay of tau M. The propagated signals are represented by xm. By setting arbitrarily the first microphone as a reference, which sets the timeline for processing, and adding a noise term, which is usually assumed to be additive white Gaussian noise, independent and identically distributed with respect to other microphones, we get the actual signals that are received in each of the microphones, which are described by ym. Now, a common approach to perform the localization is based on defining a spatial power function, which is maximized in the actual source location, and then finding this maximum. One known such function, called steered response power, or SRP, which describes the output power of a delay and sum beamformer that is steered to each point in space. As we can see here, for each hypothesized location R, the function is the output power of a beamformer or delay and sum beamformer. The estimated location is then found by the maximization of the SRP function. Furthermore, the SRP function may be calculated very efficiently by means of geometric projection in the frequency domain. As we said, the constellation of microphones in the array highly affects the SRP function. Specifically, it affects the peak shape in the vicinity of the source location, which is crucial for localization in noisy environments on which this peak blurs, and the likely error depends on the sharpness of this peak. Furthermore, different array constellations give sharper peaks in different spatial regions, which means that different arrays suit different regions. As we can see in the figures that we saw earlier, the SRP function is described as the color map. And in the uniform linear array, the region of large values of SRP is much larger than the same region for the distributed subarrays. And so the localization performance for the distributed subarrays is much better. So our motivation is to design a sparse array bound to a certain region for optimal localization performance under a given source location probability distribution function. For the optimization, we first wish to quantify a likely error region size. In order to do that, we first define the error region by looking at the SRP function as proportional to the probability distribution, the spatial probability distribution of the localization. Then we can calculate a threshold T, which is a fraction of the maximal power. And then we define the error region as every point in space in which the SRP function is larger than the threshold. Then we can define the power spread, which is a quantification of the size of this area. To do that, we estimate the covariance matrix of the points in the error region. We then diagonalize these metrics to find the principal x's and the corresponding variances and standard deviations. The power spread is then defined as the product of twice these standard deviations times the coefficient that translates this product to a volume of an ellipsoid. This depends on the dimension of the problem, which is stated by n. For example, in 2 dimensions, the principal axis and the standard deviations induce a distribution ellipse that contains the likely region of localization. The power spread is then the area of this ellipse. As we can see on the figures that we saw earlier, the distribution ellipse is described by the black line, and we can see that the spread, which is the area of this distribution ellipse, is much smaller for the distributed subarrays than it was for the uniform linear array. We can now introduce an algorithm for the array design. Our algorithm is called minimal spread algorithm and is a greedy algorithm which is based on the power spread. This algorithm takes the following inputs: a probability distribution function of source location, which we will give examples to in the simulation section ahead, number of randomized source locations that will be used in the optimization, potential microphones locations grid, which meets the desired deployment region constraints, and finally, the number of microphones in the final array that we are designing. The goal of the algorithm is to design a K microphone array that minimizes the power spread in the likely region of source locations. The idea behind the algorithm is to iteratively add microphones to the array such that each microphone minimizes the average power spread given all previous microphones in the array, where the average is being done over the randomized source locations. Here is a brief description of how the algorithm works. We randomize NRS source locations based on the distribution function that we gave to the algorithm. Then we initialize the array with the first microphone and remove it from the grid. And then for each additional microphone K that we wish to add, we go over all the random source locations, and over all the remaining grid points. And for each, we append the grid point to the array temporarily and calculate the SRP and the power spread. Then we search for the grid point that minimized the spread for this given source location, and we increase a histogram for this microphone. And after going over all the source location, we take the microphone that appeared most frequently in the histogram. meaning the maximum of the histogram. And this is the microphone that we add to the array in each iteration. After performing k iterations, k-1 iterations, we have the desired array. For performance analysis, we perform simulations in MATLAB environment. We used the standard speech signal and processed it in the short time Fourier transform domain. For parameters, we used a 9 microphone array being chosen from a 27 points grid and used 10 different randomized source locations. We restricted the deployment to a specific rectangular and added a white Gaussian noise with signal to noise ratio of 0 dB. For source location distribution, we used two types. The first was uniform distribution, which means no priority, over a rectangular space outside of the deployment region. The second was an angle priority that suits the case in which the array is deployed in a corner of the room and the localization is desired for the center of the room. Our algorithm was compared to two other types of design: uniform linear array design, growing from the center outwards, and random array design, which was averaged over 10 different designs. This entire process was repeated 10 times, and the average performance for each method was measured. Here are the results of the simulations. First, on the left, we can see the angle priority function over the space that we saw earlier, described by the color map, where the yellow color states a higher probability of source location. Second, we have the grid of potential microphone positions, described by the black squares here. And last, we have the randomized 10 source locations, which corresponds very well to the angle priority function that we used. Here on the right, we can see an example for the histograms that were calculated to choose the microphones in two different iterations of our algorithm. In each of them, in the adding of the second microphone and adding the third microphone to the array, we can see that there is a notably preferable microphone, which appears for most of the sources as the best microphone, which minimizes the most significantly the power spread based on the previous microphones. In this figure, we can see how the size of the distribution ellipse, meaning the power spread, changes when adding microphones to the array using each of the design methods. We are presenting three different iterations, which mean different microphones that are being added to the array, from left to right, for the second, third, and fourth microphone. And we are presenting our algorithm in the top line, the random design in the middle line, and the linear array on the last line. We can see that the distribution ellipse size, and so does the power spread, decreases most significantly for our algorithm when compared to the random and linear design. Here, we present the performance of the array during the entire process of design for all the three methods. In the top two figures, we can see the average power spread for the angle priority and for the uniform priority during the design iterations, meaning the number of microphones in the array. And we can see that our algorithm in the blue line provides the minimal power spread, minimal average power spread for the entire design process for each number of microphones in the array. Furthermore, the average localization error in the bottom two figures, although not directly measured and optimized by the algorithm, is still shown to be minimized by our algorithm for the entire process of design, which means for every number of microphones within the array. To conclude, our motivation was to design a practical sparse array within a given bounded deployment region for optimal localization under a given source location probability distribution. We introduced a measure for quantifying the likely error region size called power spread and used it in a greedy algorithm for array design that was called minimal spread algorithm. Our algorithm was analyzed in simulations with comparison to uniform linear array design and random design, and outperformed them in means of both power spread and average localization error. Thank you for listening.